And welcome back to Net 125. Mr. Armke here with you again for Module 7, Ethernet Switching. So let's go on and get started. So we're going to talk about how Ethernet works in a switched network, meaning that we're working with switches that are able to store information about the devices that are connected to them in order to enhance the efficiency of their operation. So we're going to talk about the Ethernet frame and how the different sublayers are related to the frame fields. We're going to look at the MAC address, we're going to look at the MAC address table, and we'll look at some different speeds and forwarding methods for working in layer 2. So 7.1 is all about Ethernet frames, the PDU that belongs to layer 2. So Ethernet operates in both layers 1 and 2. The 802.3 standard covers the physical layer as well as half of the data link, the MAC sublayer, of course, and then the LLC has 802.2. So it is a family of networking technologies that intertwine across the two layers. As we looked at last lecture, we can see that this table indicates the various protocols that may be employed to allow the MAC sublayer of data link and the physical layer to interact, and then the LLC sublayer is pretty standardized when working with layer 3. So the LLC gives us information to identify the network layer protocol used for the frame, and then the MAC sublayer will deal with our encapsulation, MAC access, as well as data link layer addressing. So 802.3 as a standard includes the Ethernet frame, which is the internal structure of the frame itself, the addressing, which includes our source and destination MACs to deliver the frame from NIC to NIC, and error detection, including what's called an FCS, or frame check sequence. And this is part of the trailer, which is only available at layer 2. So the MAC sublayer gives us a number of different specifications for things such as 802.3U, Z, AB, AE. It becomes kind of an alphabet soup after a while. But the idea is the interaction between the physical layer and the MAC sublayer allows us to identify these different subcategories of Ethernet. So legacy Ethernet using bus topology is a shared half-duplex medium. And then, of course, that deals with the contention-based access we talked about before. Modern LANs, however, have to use full duplex switches. And with full duplex switches, we do not require collision detection. So the frame is determined by not only its content, but by its structure. So the traditional Ethernet frame, Ethernet 2, is 64 bytes at the minimum and 1,518 at the maximum. So it is going to have a preamble here, 8 bytes. That is not included as part of the size measurement. The destination source and MAC are, so that's 12 bytes. The type and 2, the data anywhere from 45 to 1500 bytes in order to make sure the padding is accurate, and then the 4-byte frame check sequence at the end. Any frame under 64 bytes is considered a collision fragment or a runt frame and is discarded automatically. Frames over 1500 bytes are considered jumbo or baby giant frames and are only able to be processed in specific infrastructures. Other than that, again, discarded. Anytime that a frame goes above minimum, below minimum or above maximum, it is discarded. Drop frames are likely to be collisions or other unwanted signals and are therefore considered invalid. That's why we don't try and process them further. So let's take a look at the MAC address, Media Access Control Address. A MAC address consists of a 48-bit binary value expressed in 12 hexadecimal values. Given that 8 bits is a common binary grouping, binary all zeros to all ones can be represented in hex as the range 00 to FF. When using hex, we often make sure that we include leading zeros to display complete 8-bit representation. Whereas in binary, we would have 00001010 only shown as 4 digits, 1010. In hex, for completeness, we will often include the leading zero there, 0A. So for an 8-bit or byte representation, we will include that leading zero. Hex numbers are often represented by the value preceded by 0x. So 0x73 is the representation they give us in this example. And that helps us to distinguish between decimal and hexadecimal. Decimal 73 is very different than hexadecimal 73. So if we were to compare the two, hex 73, if we were to convert it to decimal, is, let's see, 7 is 111, 3 is 0011, so that's 64, 32, 115. So 73 in decimal is not equivalent to 115, so hex is a completely different number system, which we obviously talked about back in chapter 5. Hexadecimal can also be represented by a subscript of 16 or the hex number followed by an H. These are less common, but we will see them on occasion. In every LAN, every device is connected to the same media. MAC addressing provides identification to OSI layer 2 to talk about what device is being dealt with, and because we are going from device to device when we're dealing with switching and routing, that is the first one we want to deal with when we start peeling off the layers of the OSI. A MAC address is 48 bits long, expressed in 12 hex. As a byte equals 8 bits, we can also say it is 6 bytes in length. All MACs must be unique to the device or interface, and to ensure this, they have a two-part generation system for all network interface cards. All device vendors have to register with the IEEE to obtain a unique 6 hex or 3 byte code called the OUI, or Organizationally Unique Identifier. A MAC address will consist of the OUI code followed by a further 6 hex digits as a vendor assigned value. These are often what's called the interface ID. So for every OUI, there are 6 hex values worth of interfaces, and multiple OUI codes are often assigned to the same vendor. So if you were to go and look up, say, like Dell or Intel, they probably have several ascribed to them. Now, when a device is forwarding a message, the Ethernet header includes both a source and destination MAC address, where it's going and where is it coming from. When a NIC receives a frame, it'll match the destination MAC to see if it matches the physical address stored in RAM. If there is no match, the frame is discarded. If there is a match, it passes the frame through the OSI layers to de-encapsulate. Now note, a NIC will also accept a frame if it is a member of the correct broadcast or multicast group. Broadcast, of course, going to everybody, multicast having a specific subset of subscribers. Any device that is the source or destination of an Ethernet frame must have a NIC, therefore it must have a MAC. So that can be a workstation, a server, a printer, pretty much anything. In the example of the text we see here, we have a destination address of all C's, source address of all A's. If we look at H1 and H2, H1 is our originating source. I don't know why they clipped out the text. H2 is all B's. H3 is all C's. H4 is all D's. So H3, because it's all C's and it matches the destination address, will say, hey, this is mine. I'm going to take it in and start processing the de-encapsulation. In Ethernet, different MAC addresses are used for layer 2 broadcast, unicast, and multicast communications. A unicast MAC is when the unique address is generated for a frame sent from a single transmitting device to a single destination device. So that is the physical MAC that is used. That when we talk about the MAC that is stamped in, that is your unicast. Now the process a host uses to determine the destination MAC associated with an IPv4 address is called ARP, or Address Resolution Protocol. The process used for IPv6 is called neighbor discovery. So if you hear about ARP versus ND, it's just going to tell you which version of IP you're working with. They're the same general process, kind of like when you hear time to live or TTL versus hop limit. Now, broadcast frames are received and processed by every device on the LAN. It may be that once it gets to the point where it says, oh, this is a broadcast item, I'm going to de-encapsulate it, it may reach a point where there's a trigger that says, oh, it doesn't belong to me because of X, Y, or Z. The destination MAC of all Fs, 48 ones in binary, is then flooded on all switch ports except for the incoming port. It is not forwarded by a router, it is only handled by a switch. If the encapsulated data is an IPv4 broadcast packet, this means the packet contains a destination address that is all ones. So that means all hosts which will match the subnet mask, and then therefore the host and destination IDs will receive and broadcast the packet. A multicast frame, which again is a select set of subscribers, is going to have a destination MAC address of 01005E. whenever the encapsulated data is an IPv4 multicast packet. And if it's IPv6, it'll be 3333. So it just depends on whether or not we're dealing with version 4 or version 6 again. Now there are other reserved multicast destination MACs when the encapsulated data is not IP. So if we're using something like Spanning Tree Protocol or STP, those multicast addresses will be slightly different. We can see here in the graphic, the destination MAC on the far left starts with 01005E, and then we have our interface ID as the last 6 hex bits. It is flooded out of all Ethernet switch ports except for the incoming port, unless the switch is configured for multicast snooping. Again, not forwarded by a router. Multicast is contained to a local network only, unless, of course, the router is configured to route multicast packets. This is not a common happenstance. Because multicast addresses represent a group, they can only be used as the destination. The source has to remain unicast. As with unicast and broadcast addresses, multicast IP must have a corresponding multicast MAC. And that's the kind of thing you'll learn when you're going through the OSI layers and when you're studying this stuff. Everything has to fit together. It's very important to be able to get to know so that we can reject packets that don't belong in a particular way. That's how switches and routers and any kind of multi-layer device or other interconnectivity device can deal with replicating the necessary network flows to send data where it's supposed to go, so that we can have a MAC table that is accurate. We're able to transmit data accurately. We're able to reject frames that we don't need to save bandwidth, things like that. Speaking of, let's take a look at the MAC address table. How do we filter stuff? A Layer 2 Ethernet switch uses Layer 2 MAC addresses to make forwarding decisions. It is completely unaware of what protocol is being carried in the data portion of the frame, so it has no idea whether it's IPv4, IPv6, or an ARP message. The switch is going to make its decisions solely on the MAC address that is given. And that's only at Layer 2. It won't peel down to Layer 3. Now there are multi-layer switches, sometimes even Layer 3 or Layer 4, what are called content switches at Layer 4. That will give you the ability to make some different switching decisions. But the forwarding decisions and predominant implications today are done based on MAC addresses only. So an Ethernet switch will receive a frame, see the MAC address of the destination, and examine its own MAC address table to make a forwarding decision. Unlike a hub is sometimes called a dumb switch, simply because it doesn't maintain a table. It just broadcasts everything that it gets, except for, of course, the incoming port. Now, when a switch is turned on, the MAC address table is empty. There's another term we may occasionally use called a content addressable memory table, or a CAM table. So don't be surprised if you see that. That's not a typo. It's just another term for the same thing. So let's go through the learning process here. Every frame that enters a switch is checked for new information to learn. It does this by examining the source MAC of the frame, as well as the port number where the frame entered the switch. If the source MAC does not exist, it gets added to the table along with the incoming port number, so that says which port is connected where. If the source MAC address does exist, the refresh timer for that entry gets updated. So every 5 minutes, by default, most switches will go ahead and clear out anything that has stopped transmitting information. This ensures that old data doesn't get transmitted to the wrong place. Now, if the source MAC does exist in the table, but it's on a different port, this is treated as a new entry. So if you were to go in and take a laptop and plug it into every port on a 24-port switch, let's say, if you were able to do it all within 5 minutes, every single port would have the information necessary. But in that case, what it would do is compare it to the timer. That entry would then be flushed out because it no longer needs to be retained. So it'll go ahead and compare it and flush it out. Even smarter Macs now have a detection-based system that allows them to immediately clear a port if the connection is lost. Now let's go through the forwarding process. How do we find the destination? If the destination MAC is a unicast address, the switch is going to take a look between the destination MAC and an entry in its table. If the destination MAC is in the table, we get forwarded on the correct port. If not, we do a broadcast and try and do what's called an unknown unicast. Now, if the destination MAC is a broadcast or multicast, we do the same flooding. It's just not going to try and find the entry first. As the switch receives frames from different devices, it can populate its MAC address table by examining the source address of every frame. And when the MAC address table contains the destination, it can then filter out the frame and be able to forward it to a single port. It eliminates the need for broadcasting. So let's talk about even just this 4-port system that we've got right here. This 4-port switch. If we have these 4 devices connected, once the device has learned the MACs and corresponding connection ports for each of them, we are able to save at least 75% of our bandwidth, because only things that are unknown would need to be broadcasted, unless they were specifically a broadcast item, which would not save us anything anyway. It was going to be a broadcast regardless of whether or not it knew where the connection was going. So we see here in the graphic we have a destination MAC of 00OD, source MAC of 00OA. So we can see 00OA is our port 1, brings it in. The MAC table knows 00OA is port 1, 00OD is port 4, so we're going to slide over to port 4, and boom, we're going to deliver the information as needed. If we had the same thing and it was moving to C or B, wouldn't matter. If it was a broadcast, it would go to everybody. Again, it would be determined by an interaction of what type of address is it based on the recognition algorithm, as well as our MAC table. Okay, and then of course the thing that everybody wants to know is speed. How fast can my switch go, and how does it forward information back and forth? So store and forward switching is one of many methods that is presented. It's considered to be very thorough, but of course then there's a lot of overhead. How does it work? Well, store and forward is going to receive the entire frame and compute the CRC, or cyclic redundancy check. If it's valid, the switch is going to look up the destination address, which determines the outgoing interface. Then we forward the frame. Now, a big advantage here is that it determines errors before the frame is repropagated. So when an error is detected, it's going to go ahead and just kick it out, and it reduces the waste of bandwidth that is being monopolized by corrupted data. Now, store and forward switching is required for what we call QoS analysis, quality of service, on a converged network where we have to classify frames for traffic prioritization. So if we're not trying to prioritize devices, but instead are trying to prioritize services, we have to use store and forward. So VoIP data streams, of course, are an example of a specific type of traffic that we might frame classify, and versus web browsing traffic that would use, port 80 or something similar, we would then need to shift priority there for VoIP. There's an alternative called cut-through switching, which starts forwarding the frame before it's entirely received. So let's say that we have a full sub-jumbo frame, 1,518 bytes. Once we hit the first 64 bytes or so, what we need to bring in the message for the destination MAC, it'll go ahead and read it in, and then send it straight out. So at a minimum, the destination address has to be read, and then the frame can start forwarding as it's still coming in. Now in cut-through switching, the switch acts upon the data even though the transmission is not yet complete. This means that errors could be propagated. This means that collision fragments could also be propagated. So we want to be cautious with that. There is a middle ground, so we'll talk about the two types of cut-through switching that we vary it. Fast forward is going to start padding after the destination address goes in. It'll start sending out the individual bits, and the destination NIC will often receive a faulty packet that it can then discard. If it works, however, you are cutting down some serious lag time, some latency. Fragment-free switching is a compromise. If we have a high latency and integrity system like store and forward, but we want the speed of fast forward, we can perform an error check on only the first 64 bytes because that's where most of the errors and collisions will occur. So that allows us to forward it on knowing that by and large, the odds are that our frame should be in good shape. Now on a switch, we have what's called memory buffering to allow us to speed destination port switching due to congestion. So if we have what's called port-based memory, this means that frames are stored in queues that are specifically linked to a particular port. A frame is transmitted to the port only when all the frames ahead of it have been successfully transmitted, and it's possible for a single frame to actually delay all the frames in memory because of a busy destination port. This delay occurs even if the other frames could be transmitted. So it's almost like going to the bank, and instead of it going from, okay, next person in line please, the person who's there, basically completely throws off the scheduling for everybody else, and they, have to focus on this one person. Shared memory is a little bit different. We take all of our frames, dump it into a common memory buffer, and then the amount of buffer memory required by a port is dynamically allocated. So if one particular port requires a substantially larger amount of memory, we can still keep a minimum amount on the other ports and allow traffic to continue flowing. So basically we can dynamically link the buffer frames to be able to transmit things from one port to another without having to move it to a different queue. So as I said, this buffering process may occur whenever destination ports get busy. Shared memory buffering also results in larger frames transmittable with fewer drops. This is important with what's called asymmetric switching, meaning that different ports can have different data rates, so that we can prioritize traffic a little bit differently. Two of the most basic settings on a switch are the bandwidth, which is what we think of as speed, and then duplex settings. Now, we just talked about duplex last chapter, so of course it's important that we understand that full and half duplex be negotiated correctly. If we have half duplex on one side and full on the other, we could have a lot of collisions, because full duplex will not have any pausing waiting for the half duplex item to transmit. Auto negotiation is an optional function on most switches and NICs, but it's almost always going to be turned on. Now be aware, if you're using a gigabit system, these only operate in full duplex, so there's not going to be any worry about auto negotiation for those. Duplex mismatch is graphically represented here. We can see that the link is never clear enough for the half duplex device to stop getting collisions and be able to send what it needs. On 10 base 100 megabit Ethernet links, this is pretty common. If both ports on a link are reset and the auto negotiation process doesn't catch that there is a difference in the transmission preferences, you can start getting a lot of collisions. So the best idea is you can just right click, disable, wait about 5 seconds and re-enable, and that'll usually fix it. Again, we should make sure that if auto negotiation is enabled, that it's either everybody has it or nobody has it, so that way we can make sure everything's transmitting. There are very few reasons I've run into with a modern switch or other link to put it in half duplex mode, so I would just leave it in full duplex if that's the default. There's also something we use called Auto MDIX, Automatic Medium Dependent Interface Crossover. Connections between devices used to be that you had to specify based on the device what kind of cable you would need to use. If it was a PC to PC, you had to use what was called a crossover cable. If you were connecting from a host to a switch, you could use what was called a straight through or patch. So Auto MDIX can automatically detect the type of cable connected to the port when it starts to boot. By default, any switch running Cisco iOS 12.2 or later will have it, but the feature could be disabled. So just be aware, Auto MDIX is nice, but is not always going to be there to save you. So if you start having connectivity issues, be aware of what type of cable you're using and make sure that you change that accordingly if you have problems. Here are some new terms and commands we covered this chapter: store and forward, cut through, fast forward, ARP and ND, fragment-free switching, the OUI. You may also want to be aware of the interface ID, port-based memory, shared-based memory, and Auto MDIX. A little bit longer than last chapter, but this time we kept it under a half an hour. So hopefully this was very instructive. If you have any questions or concerns, as always, you can contact me via email at jermke063@cfcc.edu and my Google Voice number 239-7814. Hope you guys have a great rest of your day, and I'll catch you next class.